So welcome to SAMPE Q&A session for additive manufacturing, and thank you all for joining us. I would like to make you all aware that this session will be recorded and posted on the SAMPE website for on-demand viewing. If you have questions throughout the duration of this session, please type them in the Q&A feature found on the control panel of your Zoom meeting window. I'm Chris Locke, SAMPE's Director of Marketing, Membership, and Education. While I started my career in tech, I am not an engineer, which is why you'll hear me stumbling on some of the upcoming acronyms and Latin-like technical terms that we'll be mentioning in today's Q&A. Feel free to laugh. I know I probably will. Feel free to correct me. And generally approach this session as a fun but intensely valuable learning experience. I know I will. So with that, let's begin by introducing our panelists for this session. I'm going to start with Scott Huelskamp, who's with the University of Dayton Research Institute. Mr. Huelskamp is a team leader and composites engineer at UDRI, specializing in advanced polymeric manufacturing techniques. It's begun already, including the design, fabrication, and use of additive manufacturing tooling. He has successfully directed millions of dollars of previous R&D efforts and has almost 15 years of composite manufacturing and tooling experience. He is currently leading an additive manufacturing tooling development program for Airbus's Wing of Tomorrow program. Mr. Huelskamp holds a bachelor's degree in mechanical engineering and a master's degree in materials engineering from the University of Dayton and is a registered professional engineer in the state of Ohio. His paper is titled Hybrid Additively Manufactured Tooling for Large Composite Aerostructures. So welcome, Scott.
Thank you.
Yu-Chuen is with the University of Texas at Austin. Yu-Chuen Chang is a PhD student at the University of Texas at Austin, also known as UT Austin, who received her bachelor degree in mechanical engineering from National Cheng Kung University, also known as NCKU, in Taiwan, and her MS in mechanical engineering from UT Austin. Her research interest is on reverse engineering and computer-aided design for additive manufacturing. The title of her paper is Additive Manufacturing of Multifunctional Lattice Structure-Based Concepts for Thermal Protection System. Welcome, Yu-Chuen.
Thanks.
Next is Stephen Kim with the University of Texas at Austin. Stephen Kim graduated with a BS in Mechanical Engineering at UT Austin and began working with Dr. Joseph Koo on polymer nanocomposites during his undergraduate studies. He has extensive knowledge in additive manufacturing from working as a manager of the Texas Invention Works Maker Studio at UT Austin and has also continued to work on numerous polymer nanocomposite projects with the Koo Research Group after graduation. His paper is entitled Additive Manufacturing of Polyimide 6-66 Copolymer Nanocomposites, Thermal and Flammability Properties. So welcome, Stephen.
Thank you.
And Tristan Bacha is with Rowan University, Department of Chemical Engineering. Tristan is a second-year PhD student studying cold spray additive manufacturing. He received his bachelor degree in chemical engineering from Rowan University in 2019. Tristan's interest in manufacturing began after spending a summer at the Viking Yacht Company in New Gretna, New Jersey. He chose to pursue a PhD after gaining research experience with the Mora Letts Group and the Sustainable Materials Research Laboratory at Rowan. His paper is entitled Cold Spray Additive Manufacturing of Polymers. Temperature Profiles Dictate Properties Upon Deposition. So welcome, Tristan.
Thank you.
Okay, so we've introduced all of our panelists. Brianna, did we have Reza join us?
I see Frank Abdi's name, but go ahead and just introduce Reza. Frank, I see you unmuted yourself there. Is it Frank or Reza that's with us here?
Hi, this is Reza.
Hi, Reza. Welcome. Okay, go ahead, Chris.
Hi, Reza. So Reza is with the AlphaSTAR Corporation. In his biography, he is a mechanical engineer at AlphaSTAR Corporation with a background in additive manufacturing and composite structural analysis. Having earned his MS in mechanical engineering from Cal State University, Long Beach in 2018, and working as a research assistant at the Advanced Manufacturing Laboratory at Cal State Long Beach, Reza's research was focused on novel methods in 3D printing of metal matrix composites using jet binding technology. Now, Reza uses his knowledge about material characterization, performance validation of continuous chopped and braided composites with complex structures, 3D printing simulation and part qualification of prevalent polymers and composites in an additive manufacturing industry to bring value to the AlphaSTAR team. His current focus is using integrated computational materials engineering, ICME methods, and multi-scale progressive failure, MS-PFA techniques to benchmark new material systems and solve complex problems in additive manufacturing. His paper is entitled Additive Manufacturing Ultim 9085, Part Qualification and Allowable Generation. So welcome, Reza. Okay, so we're going to begin by asking the first speaker a question, and then we'll kind of continue down with the questions. We have several questions for each of our speakers. So Scott, I'll start with you. If you can, talk more about the hybrid additive manufacturing tool. What exactly does the hybrid refer to?
Yeah, sure. So hopefully, if you're on this webinar, you've listened to the presentation or reviewed the paper that I had submitted. But essentially, what we're doing, we're looking at cost and time-effective ways of making tooling for large aerostructures, large composite aerostructures that would really be a cost savings measure over your conventional tooling approaches. So the hybrid part of it is really an acknowledgement that additively manufactured AM tooling has plus and minuses just like every other technology. So what we are doing is hopefully taking the strengths of the AM approach and augmenting them with more of a conventional tooling approach. So you get the strengths of each one, which balance out the weaknesses of each one. And that would be, in a nutshell, what the hybrid means.
Excellent, thank you. Yu-Chuen, I have a question for you. Is there any relationship between the crystallinity of PEKK and the resulting ablation performance?
Yes, let me share my screen with you really quick. Screen share.
Perfect, it's coming up. There you go.
Okay, thank you so much. So actually, we have done research on the Annealing PEKK before, and you could see on the right side, which is the photo of our previous Annealing PEKK sample. And in this test, we are testing the heat with the 100 watt per centimeter square heat flux for 50 seconds, 30 seconds, 60 seconds, and 120 seconds. And at this time, we didn't investigate any split and melting issue for our PEKK sample. However, for this time, we are using annealing PEKK. And so in this time, we only testing 30 seconds, but we do see some of our sample, even the solid one, have some split and melting. And so it's kind of explained that the annealing improve the thermal resistance of the PEKK material. And it's also commonly for most of the, it's also common for most of the polymer we using annealing and try to intend to improve its thermal resistance or mechanical property there.
Excellent. Thank you. So I have a question for Stephen Kim. This one is asking, what's the difference in terms of printability between NEAT PA666 and the FR formulations? I guess FR is flame retardant, right?
Yes, so FR is flame retardant, and Basically, the main difference between the printability of the two is that the neat system, which had no additives added into it, those were significantly easier to print than the flame retardant formulations. And this was mainly because the FR formulations have a lot of other additives in there, like carbon fiber and elastomers and such. And with those additives, it increases the viscosity of the melted material. And so the printer just had a harder time pushing out the material with the same settings as the neat system. So in the end, we would need to apply some further adjustments to the 3D printer itself to make sure that the FR formulations can print at the same printability that we see in the neat system.
Mm-hmm. Excellent, thank you. Tristan, question for you. Would it be beneficial to discuss some limitations of these assumptions, like no representation of mock diamonds?
Sure, yeah. I'll share my screen real quick to elaborate a little more. Can you see all right?
It's coming in. There you go.
All right. So the question about mock diamonds would be, at the exit of the nozzle, we might see some overexpansion or underexpansion effects. And right now, we're actually looking at similar results to what we formulated here, except with the gas represented by a CFD simulation. And we're actually finding that these simulations compare quite nicely with the 1D simulations. Another major assumption I think is worth discussing here is that not only are we, in this case, neglecting the mock diamonds, but we're assuming that there's some region where the gas compresses in front of the substrate. And that's going to be different in reality, obviously, to here, but we're actually seeing that our simple assumption is comparing nicely to what we see in CFD results.
Can you talk a little bit about which industry this is targeted toward?
So we're actually targeting composite manufacturing and repairing composite structures for the Army.
Oh, interesting. Excellent. Thank you. Reza, question for you. Why did you choose Ultim 9085 for your study?
Thank you for the time that you've given me. So basically, we collaborated with NGC, Northrop Grumman Company, an FDM-based AM research program, and it was their material of interest. So as you may know, Ultim 9085 is a flame-retardant, high-performance thermoplastic for digital manufacturing and rapid prototyping. It's ideal for the transportation industry due to its high strength-to-weight ratio and its great flame, smoke, and toxicity rating. And these unique materials certifications make it an excellent choice for the commercial transportation industry, specifically in aerospace and ground vehicles. AM printing of Ultim 9085 resin allows design and manufacturing engineers to produce fully functional parts that are ideal for advanced functional prototypes or end use without the cost or lead time of traditional tooling.
Excellent, thank you. Scott, we'll take it back up to you. I have another question for you. How about the speed by using 3D printing? Is the manufacturing time taken into the cost savings calculation?
It would be taken in indirectly. So the cost, the number one goal that we had in the project, other than having the performance of the tool matching a conventional tool, was looking at the cost. So we tracked all the costs that went into our tool, and then compared that to an actual quote from a tool builder to see what efficiencies or what savings we could have. So when I say that it's included, a big proponent of the cost in a conventional tool, I would say actually most of the cost, is the amount of time that tool spends on the machine. So there's an hourly rate or a shop rate usually that would be applied. So the longer it takes to machine, the higher that cost would be. With our approach, you have hourly fees as well. There is some machining, a lot less machining, so the hourly rate is lower. And then there'd be an hourly rate associated with the 3D printing of the tool as well. So we took commercial rates. So in both cases, we used rates that anybody off the street would, if they were to buy this tool, they would use those, they would get those rates. These wouldn't be university research rates. And we compared the tool, so compared the two. So we saw a 50% savings by compiling up all those numbers. So I think that answers your question, Chris.
Very much so, thank you. Yu-Chuen, question for you next is, instead of using existing lattice structures, is it possible to further optimize the lattice structure for this type of application?
Yes, let me share the screen really quick.
Please. There you go.
Okay, so when we consider the lattice structure for thermal application, we need to separate the problem into two types. First is steady state problem, and the second is transient problem. And for the steady state problem, if we look at the existing literature and based on our study, generally, when the density decreases, the thermal conductivity decreases. But for the transient problem, you could imagine the role of thermal diffusivity is also important. And thermal diffusivity is the ratio of thermal conductivity and density. So when the density and thermal conductivity both decreasing, there is no guarantee we really get the minimized thermal diffusivity. And so the whole idea for the lattice structure design for the transient problem, for example, like the thermal protection system, is try to find whether we could tuning the relationship between the thermal conductivity and density in order to minimize all the thermal diffusivity of the lattice structure. And recently, we using the finite element analysis and to simulate our proposing lattice structure. And we found that we compare with a simple cube, which you could see on the screen. We found that our proposing design potentially might have the identical thermal conductivity compared to the simple cube lattice, but even lower the thermal diffusivity. And we plan to publish the relevant study in the end of this year.
So kind of a follow-up question, can you give us some examples of how this can be used in different industries or applications?
Yes, so first, in this application, we will try to targeting on the thermal protection system. And so one of the beneficiaries to using lattice structure is first, we could using single material instead of multiple material. And for the single material, there is a couple beneficiaries. First, there will be no requirement for extra adhesive or bonder. Second, you could imagine if we have a dual material, it might be more challenging to predict the actual material property, especially between the boundary of two materials. And with the lattice structure with single material, they might be easier to predict the overall material property there.
Thank you, Yu-Chuen.
Thank you.
Stephen, another question for you. What's the UL 94 rating of NEAT PA666?
So I'll share my screen here real fast. All right, so this is my the current slide for the UL94. And for the NEAT system, of PA666, as well as any other nylon system, is V2, which is the lowest category of UL94. And with all NEAT nylon systems, we see that they all exhibit properties of that exceed past V2 actually. So we find that they all take a significant amount of time to self-extinguish after they've been ablated, and they all tend to melt and drip onto the cotton indicator and then cause a second ignition. So the short answer is the UL94 of NEAT 666 is V2.
Got it, thank you. Tristan, question for you. What is the meaning of 1D mentioned here? In real case, it is a 3D pring, So any comment about how to improve your model?
Sure, I'm going to share real quickly. So the 1D refers to how the gas properties are calculated inside the nozzle. So the one dimension is just the length from the entrance of the nozzle up to the substrate. So this at each distance, there's some area ratio that is used to calculate what the pressure, velocity, and temperature of the gas is. So that's the one dimension there. In improving the model, we're currently looking into using CFD simulations to sort of capture what differences lie in sort of the radial direction along the nozzle and, as before I touched on, outside of the nozzle itself.
Great, thank you. And then Reza, I have a question for you as well. Any plans to repeat the testing with other thermoplastics?
So in our future roadmap, basically we are planning to benchmark other common polymers such as PEEK and PEKK, and we're already investigating on other interested materials. We have published several papers in AM material modeling, and for example, for on-field polymers such as PA11, PA12, Altum 1010, and ABS, PLA, and also some field materials, field polymers such as nylon 12CF and ABS CF material systems. And we are planning to benchmark other materials as well.
Excellent, thank you. So we have a question that came in, and I think it's for the good of the whole panel, so we'll have you each respond to this. Let's start with you, Scott. What would you say was the one of the most surprising or interesting discoveries with your research?
Interesting discoveries. So we didn't go into it a lot in the paper, but we took kind of a parallel path approach. So if you're familiar with what we did in the paper, we 3D printed a tool core and then made a sandwich structure with it by laminating it top and bottom with a tooling prepreg. And that whole sandwich structure essentially became the tool at that point. So in parallel to that, we looked at another approach that would be maybe more in line with how a conventional composite tool would be made, in that we made a master. In this case, it was a 3D printed master, and then laminated the composite, or the tooling prepreg onto it. And then rather than trying to get it to stick to the 3D printed core, we had it pop off and demold from that structure, and then that became the tool. So one had the 3D printed part inside of the tool, the other one did not. It was there simply to form it. And when we calculated out the costs of the two different approaches, again, we made the exact same tool geometry, just with both approaches. The costs were within just a few $100s of each other. So that was a pretty big surprise to us, and that we took two really very different tooling approaches, and the cost came to be so close. And both of them were still around that 50% savings over a conventional tool. So it was a pleasant surprise in that we have two techniques that can be used, and we can kind of switch from one to the other depending on what the part geometry is, and not have any cost implications to do that.
Excellent, thank you. Yu-Chuen, same question. What would you say was the most surprising or interesting discoveries with your research?
Yes. Would you mind if I share the screen there?
Please.
Really quick. I think first, because in this OBT test, we also modify our ablation test in order to preventing the side heating. And so in the left side, I show the solid pack result. And please, for this diagram, we only showing the location for TC1 and TC2. And so, and the right side is another our previous research with different material, but the same idea for the ablation test with different depth. I understand the color might be difficult to identify, but the top image is the 5mm away from the surface explode to the heat loss. And the second one is 10 millimeter and the bottom is 50 millimeter. Therefore, I will expect the experimental result will kind of similar to this trend. And even for the solid, like this one, you could see the trend is different. And within the replica testing, also see the similar trend there, which is mean there might be something alter the experimental result. And it will be the next step we will focusing on study there.
Excellent, thank you. Stephen, same question. What would you say was one of the most surprising or interesting discoveries with your research?
So I'll share my screen. So I'd say the most interesting bit from my project here was the difference in porosity between the neat system and the formulation that we tested. So when we ran it under micro CT analysis, we found that the formulation 5 that we tested had significantly higher number of pores in comparison to the neat system. And we found that formulation 0, which is the neat system, had all of its pores mainly localized right around the center of the sample, whereas the formulation 5, the pores were just all over the place. We just found it in the entire sample. And it's also shown again in this slide. So in the top image is formulation 0, and you can see in the cross-sectional image, it is very smooth and it's pretty solid. Whereas on the bottom, which shows formulation 5, you can clearly see in the black spots, which are all the pores. And so this led us to look at the printability of all of our formulations, which goes back to the first question that I was asked. And so this CT analysis allowed us to go back and take a look at what our printing parameters were. And so that is the next thing that we'll be modifying to make sure that the porosity of our formulations that we make closely resemble the actual neat system.
Excellent, thank you. Tristan, same question. What would you say was one of the most surprising or interesting discoveries with your research?
All right, I'm gonna pull up my screen. All right. So I would say one of the most interesting things is just with looking at this figure here, this is the temperature profile inside of a particle just when it's about to hit onto a substrate. Just by changing, say here, the initial particle temperature, we can get sort of a characteristically different temperature profile in that particle. And then looking at it when it impacts the substrate, that will greatly affect what mechanical properties we see. So this means when we're looking at cold spraying polymers, we're going to have to really carefully consider how we design our nozzles and what conditions we'll use. When looking at something like traditional metal cold spray, we found that these stratifications in that particle temperature inside of that particle really aren't that great or not really present at all.
Excellent, thank you. And Reza, you're the last to answer this question, saving the best for last. What would you say was one of the most surprising or interesting discoveries with your research?
So let me share my screen and I can show you. So you see my screen, right?
Yes, looks great.
Okay, so the most interesting thing that I did in this research was allowables prediction. So basically, we had test data from NIAR, and it was for 2 different machines, Rapid Prototype and Manufacturing and Stratasys. They printed out Altem 9085 parts with these 2 machines. And then they had certain numbers of test data, and then we could simulate numerous test samples, and then we predicted the allowables, and we could compare that with the allowables they got from test data within 10% of error. And also, we could establish the generic basis allowables and acceptance region for FDM printed Altem 9085 for those 2 machines. And it will give you the region. For example, when you print a part in RPM machine with certain material, it will tell you with 95% level of confidence that what would be the strength of the part if you would have printed that with other machine. And that's it will help the designers when they have different machines in their manufacturing facilities to predict the allowables of the parts coming out from those machines.
Great, thank you. So we had another question that came in, and hopefully we'll have time to have all of our panelists answer it. How do you see the future influence of this project? And Tristan, why don't we start with you? And again, that question is, how do you see the future influence of this project?
I think what I was touching on before is actually going to have the greatest future influence. So we're going to be able to tune these different temperature profiles in these particles and essentially get different characteristics of deposition. Now, one of the bigger problems currently in polymer cold spray is actually getting these particles to stick efficiently. So we'll be looking at targeting these different temperature profiles and mechanical property distributions in these particles and seeing what gets us the optimal deposition and moving from there.
Great, thank you. Scott, same question. How do you see the future influence of this project?
Well, you know, tooling is a huge capital investment for doing a composite structure. And when you look at an entire aircraft, especially as more aircraft move towards composite manufacturing, it represents a tremendous amount of money to tool for a new program. Any opportunity to cut out some of that initial startup cost makes it that much easier to bring in new platforms or new designs. So particularly when we look at the emerging market for urban air mobility, where their companies are trying to replace taxis essentially with flying taxis in the very near future. When they need to build up those fleets, any opportunity to reduce tooling costs will give them an opportunity to build more variants and more specialized designs that'll just increase the accessibility for the technology to be adopted by a wider range of audience. So this project, along with others that are trying to do the same thing, could have a tremendous impact on the industry, especially in that particular sector.
Fascinating. Very cool. Yu-Chuen, same question. How do you see the future influence of this project?
Yes, so I think I kind of mentioned previously is kind of, for example, using the lattice structure, we could verify the material property. So for example, we might be to create the gradient design with the single material to vary the material property based on our needs and eliminate the further requirement for the adhesive and easier to predict the overall material property. And additionally, consider the area of lattice structure. There is a lot of study on mechanical, acoustic, or even optical application. However, is really have research on the thermal application there. So we will expect our research might be provide another direction to thinking about the application of a lattice structure.
Excellent, thank you. Okay, Stephen, how do you see the future influence of this project?
So since nylon or polyamides are a fairly very widely used material, I'd say just the future influence would be seeing this material be used for anywhere from consumer goods all the way to, let's say, the aerospace industry, for anything that might require flame retardancy and the flexibility that this nylon material can provide. And because nylon 666, it just tends to have a easier printability than compared to the other nylon families, such as nylon 6 or 11 or 12. I hope that this flame retardant material might be easier to work with compared to the other nylon flame retardant materials.
Excellent, thank you. Reza, same question. How do you see the future influence of this project?
So basically, part qualification of AM printed parts is really important, and some certain stages must be passed to do that. The first one would be allowable generation and prediction. And also, as I mentioned, we need to establish a method in order to design the generic basis allowables of the parts. Also, we should use progressive failure analysis more and more to show the distortion and predict the net shape of the parts. And virtual AM simulation process will give us better understanding how the part is getting printed and how we can improve the printing parameters to have more qualified part.
Excellent. I think we have time for one last question. Yu-Chuen, I'll start with you. What are the next steps for this topic that you're working on?
Yes, so I think the first thing we will first investigate why the trend is different than we expect there. And the second, we will compare the difference between annealing and unannealing material. And the next step, we will also conduct the apparent thermal conductivity measurement to measure different lattice structure. And then finally, we will also do the research on our proposed topology and to demonstrate that the potential benefit to using like a lattice structure not existing in the nature for the insulation purpose.
Excellent, thank you so much. Reza, what next steps for your topic?
So we basically would like to continue our efforts and implement this method to predict the printing process and qualify the parts, use other AM methods and other materials.
Makes sense, thank you. Tristan, what are your next steps?
So our next steps are looking at our simulations and how they compare to something that takes longer and is a little more involved. So computational fluid dynamics simulations, and then taking our actual moment of impact particle temperatures and mechanical property profiles and looking at them in finite element solutions to how that particle deforms upon impacting with the substrate.
Excellent, thank you. Scott, what are your next steps?
Well, most immediately will be to continue the investigation on a full-scale tool. So we've gone through all the exercises to do a 2-foot long tool. We have scaled up to a 10-foot long that's was planned to be completed by now, but hit some of the delays with some of our suppliers and machine shops because of the COVID shutdowns. So we hope to be able to validate everything we did on a 2-foot tool on a full-scale 10-foot tool. And then beyond that, we will be bringing that tool to Northrop Grumman to do some of their automated composite forming processes. So we want to validate that it works well with their equipment. And then lastly, we want to mature the technology to have it be able to be adopted into a production platform, or at least a pre-production. I think at this point, we're very close to doing that. We have some loose ends to tie up though beforehand.
Understandable, thank you. Stephen, and your next steps?
So next steps would be to take some SCM imaging of all of our materials to ensure that all of our additives were dispersed evenly throughout the entire system. And after that, it would mainly be fine-tuning all of our 3D printing parameters. This would be to ensure that all of our other FR formulations could be printed, since in our first initial round, we could only print 1 out of the 3 that we wanted to print. And so it will be fine-tuning the 3D printing parameters. And then with that, we can then, if we are able to successfully print all of our samples, then we would do further fine-tuning to reduce the porosity of all of our printed samples, which we predict will affect the flammability as well as the mechanical properties of all of our materials.
Excellent, thank you. So I don't see any further questions from our audience, but I wanted to take a moment and ask our panelists if they had anything that they wanted to clarify or add on to anything that they've presented today. Okay. So with that, I want to thank everybody, the panelists and our audience, for participating in this session. If you have additional questions, feel free to fill out the form on the track landing page on the SAMPE North America website, and SAMPE will follow up. Make sure to check out the content being released next week for the emerging materials and inspection and repair tracks within the virtual series. And with that, thank you, everyone.